Hey, Earth Science students. Hey, welcome back. Hey, guess who got a new toy? That's right. I've actually had it for a little bit. Um, the Earth Science videos, I don't make them as often. So actually, the bio people and the A&P people have been seeing this for a little bit. But hey, welcome back. Thank you for turning this in. Yeah, this is going to make it a little more, even more interactive than what it had been in the past. Because now you can see me and you can see all the hand gestures and the air quotes and all that good stuff. So we're going to have a good time with this. We're going to have a lot of fun. So, yes, let's get started. Oh, man. The topics we're going to talk about today, unbelievable. And the reason why they're unbelievable is because they affect you. They are a part of your lives every day. And of all the pages in the Earth Science book, textbook, if there was one page that I had to pick out that would be my favorite, it's going to be this stuff right here. We're going to be talking today about weather patterns and the way our air masses move around us, and that's going to really explain so much about our daily lives. I mean, I know you guys are younger, you got so much going on, so many interests. But someone like me at my age, weather is just a huge deal. I mean, you got to know what's going on so you can prepare and what to expect, and it affects so much of our day that it's just super important to know what's going on. And this is kind of concerning. Okay, good. All that it was grinding so much. There's been a few times where I've lost these things or just don't turn out like I need them to. And so that always worries me when I see that, or this up here usually sometimes goes red because it's not saving properly. So yeah, I don't like those situations. But anyway, hey, welcome back. Thank you for tuning this in and opening this up and playing this. Like I said, we're going to have a great time with this because we're going to explain our weather around us, and maybe even a few things about the area around Nevada. And that kind of stuff. I've always grown up, much further south. I should say much further, just an hour or so. Grew up in Joplin, live in Lockwood. If you don't know where that is, you can look it up on the map. But it's just kind of east, a little northeast of Carthage, and they follow a very specific weather pattern. Nevada's a little different, and we're gonna attempt to explain what's going on. But the prevailing thought in Nevada is that things can be all around, like in the wintertime, the snow, or storms in the spring and fall, and the summertime, and they never seem to get to Nevada. And we're going to try to explain maybe a little bit of why that's the case. But again, just cool stuff about us because. I allowed me talking to me some weather and the weather patterns and not just like temperatures and stuff, but just what's going on and why. And we're going to do that. We're going to do that today. So what you see on the screen obviously is the end of the previous meteorology video that you have watched. And so we just wanted to touch on a couple things to review because they're going to lead into what we're going to talk about today. So got my glass of water here, and so with that, we will get started. Now, what you want to remember is that the Earth is tilted, and because of that, it creates the seasons, which we talked about way back in chapter 27. But because the Earth is tilted, we get that uneven heating, okay, again, which we talked about in chapter 27 when we were talking about how the Earth rotates around the sun. And we got our little reminder about our tilt here, 23 degrees. My generation, we just said Michael Jordan. Your generation would be LeBron James. And so, but that's the idea behind that 23. And we talked about the air masses, the different types, and where they are or what they look like on the globe. Yeah, excuse me for a second. I know for some reason I was getting a little chilly there, so I had to turn off the ceiling fan. But that's the idea of how this leads into our topic today. So let me take all this and slide it over there. Yeah, look at that good teacher move right there. That's awesome. That right there, some strong teacher stuff right there. And I need a little bit more of this, so I'm going to have to go down here because I certainly don't want to get it behind here like that. Or I know you'd really be upset if I covered up the picture because, you know, I know you want to see that that face right there. So, oh, got my Earth Science green on today, so I did that just for you guys, so you appreciate that. So, let's talk. I got 1,000 thoughts there, but let's talk about weathermen. Weathermen get a bad rap on the weather. You know, the idea of seldom right. But the answer to the question, if the question is how often are weathermen correct, the answer is 100%. They're always correct, and here's why. I mean, you may think, oh, well, no, they said it's gonna rain yesterday, and it didn't rain. Well, they didn't say it was going to rain yesterday. What they said was maybe there was a 60% chance of rain. But what you got to remember, or what you got to think about, is there are hundreds of variables. Hundreds of variables. Just like in the cafeteria, they try to predict how, you know, they make the 4 or 5 things that you guys have an option of eating, and they try to predict, okay, so many numbers are going to eat this, and so many are going to eat this based on previous patterns, previous results. And some days they may run out of something that they didn't think was going to sell that much, and they may have a bunch left over of things that they thought would go big. And that's not right or wrong. That doesn't mean that they got it wrong or they got it right. It just means based on previous patterns, previous buying patterns, they tried to predict and make that type or amount of food. Okay, weathermen, it's the same thing. They take all of the data, all of the patterns that are going on, all the things that are happening, and you got to think that they've got to take into effect the what the air masses are moving, the temperature differences between areas, fronts, cold, warm, you know, the air masses, the Coriolis effect, which we're going to talk about, which you can see right there in front of you. And they take all that into consideration and try to predict what weather we're going to have. Well, when one of those changes, okay, it throws everything off. That's why if you have a weather app on your phone, or someone in your house monitors the weather pretty closely, it can change almost hourly to hourly. You know, hour to hour. We can have a situation where they're saying, oh, it's going to rain at 3, and then you look again, and now it's pushed back to 6 o'clock. Well, what that means is that the speed of the air mass reduced, so it slowed down. Or, hey, they say, oh, it could rain at 1, and it shows up at 11:30. Well, what that means, it doesn't mean that they were wrong. It means what happened is the air speed, the mass speeded up and got there quicker than they anticipated. And so that's why it changes a bunch. So that's why they're never wrong. Okay, it just the patterns changed, or some of the variables changed, and therefore created a different situation. So, but we're going to talk about several of those factors that are part of determining or trying to predict our weather. The first thing, let me get a pen here. Since I made a big deal about the green, we got to go with green, Earth Science. So we're going to start right here. Look at that strong teacher move right there. Drawing on a whiteboard, pointing at an image. That's some pretty strong teacher skills right there. So what you want to think about is, or what you want to remember, I should say, is the way we rotate. And you can see here, this little arrow here showing you is that we spin going this way. Okay, and the first thing that explains to you is why the air masses move across our area, our part of the world. And of course, you could talk about the different hemispheres and how it looks or appears in there, but we're going to talk about us. We're going to talk about our area, and people in South America, the people in the South Pole, they can talk about their weather, because it isn't so important, everybody's weather patterns, but you certainly want to know our weather patterns. So on a general day, the winds move from the east to the west, and because of the Coriolis effect, and I'll put this up here, you can see it, but our weather patterns typically move from southwest, to northeast. Oh, and let me back up and say, I know I don't always do a great job with it, and then usually somebody reminds me. Like I know in the first video I was good about giving you your pictures, but on the second one about the moon surfaces and stuff, I didn't do a good job there. But I always try to give you, so you should have these pictures in front of you. Now you won't have any of the words that I type, because that's your job to write that stuff down. But hopefully you have these pictures in front of you, so you can draw on them and the lines and stuff, and have that in front of you. So, but if I didn't, then you just need to draw these, and these are pretty simple diagrams here. But hopefully I gave those to you. So if you're sitting there, you don't have them, hopefully you have a chance to say, hey, you can give us the pictures. But hopefully I did. So, but again, the first thing, our rotation, and that causes our winds. Well, we're going to say from east to west. But because of the tilt, that's what creates the southwest to northeast. So if we weren't tilted, they would move just like this because of the rotation. But because we're tilted, they go this direction. And if you were someone who grew up in the southwest corner of the state like I did, you would know this, because your weather patterns follow that line almost to the T, almost perfectly. Growing up in that lower section down there, we call it the I-44 corridor. If you know anything about I-44, it cuts across our state just like this. And kind of a more of a diagonal pattern. You can go from Springfield, Missouri, to St. Louis on I-44, and if you know anything about our state, if I draw a square over here, if this is our state, Springfield would be here, and St. Louis is more here. So it's that diagonal line. And I don't know this directly, because I didn't talk to people who built the highway or the people that planned the highway. But you would think it would seem the reason why they created it or built it in that pattern is to follow the wind patterns, and that way at least cars going from east to west would have the wind pushing them. So at least half the traffic benefits from the wind patterns. Of course, the ones going the opposite. And of course, highways, like when you go from 49, highways that go this way or this way, then you always have the wind pushing you on the one side. So if you're driving and you have a strong wind day, you can feel your car. If you're headed from Nevada down to Joplin, it'd be pushing you. Let's see, I got to turn around here. It'd be pushing you to the left. And if you were driving from Joplin to Nevada, it'd be pushing you to the right, your right. So that's the idea of our wind patterns. So this right here is super important to remember, because, and I possibly have already started this process, but I like to ask this question 1,000 times, just so it's ingrained in your mind that our wind patterns move from southwest to northeast. In other words, from like a Joplin to a Columbia, from a Joplin to I almost said St. Joseph, that's not right. Mexico, Missouri, if you know where that is. It's up in the upper corner kind of things there. So, but that's the idea, southwest to northeast. and part of it is our rotation. The other part is the Coriolis effect, which we are going to talk about now. So these three images are all the same thing, Coriolis effect, but they showcase it in different ways. And so we're going to talk about each of them and how they can explain to you the Coriolis effect. So because we are spinning in this manner, okay, as air moves away from the equator, because that's where you have to think about the idea of convection. The idea of convection is the warm air rises. Okay, the warm air rises and pushes out, okay, away from there. Okay, moves away from the equator at that point in time. And so when it moves away from the equator, if we didn't rotate, it would just move straight up. Okay, or in this case, straight down. But it would just move straight up. But because we spin, and we're spinning in this direction, it makes it seem like, because it's not optical illusion because we can't see it, but it's a feeling illusion. How about that? The air is actually just moving straight up, but because we are rotating, it's like it's moving it. It seems like it's moving it more this way, as you can see here by that arrow right there. It just gives that illusion, because the one way of thinking about it is if the air is moving, it wants to move this way. Okay, so by the time it leaves the equator, and if it moves straight up, because what you have to think about is the air is not attached to the surface of the earth. It's not attached to it, so it can move freely. So it wants to move upward, but because the earth is spinning below it, air that is moving up here, by the time we get, if we drew the United States in a rectangle here, and if this air leaves the equator, when it leaves the equator, maybe the United States isn't in its path yet, but by the time, with the earth spinning, by the time the air gets up to the United States, maybe now the United States is here. So the air that was once ahead of us is now behind us because the earth is spinning, but the air is not attached, and so therefore it just gives that illusion, gives that feeling that it's moving at that slanted southwest to northeast feeling. And again, proof of that is how our weather patterns, like for example, I say that, but let's now talk about that. Growing up in Joplin, if we wanted to know where our storms were coming from, snowstorms in the winter or just rain any other time of year, they would always come from like the Oklahoma City area. You could just follow. And matter of fact, even on really bad days when maybe there's even tornadoes involved, if tornadoes ever reached the Joplin area, or later when I was an adult, lived in Springfield, if tornado systems or systems that could produce tornadoes were going to hit the areas I lived in, they always came from the Oklahoma City area to Joplin to Springfield, that kind of stuff. And so, but if you think about, if I draw this area as a square, and Springfield is here, Joplin is here, well, guess where Oklahoma City is? Oklahoma City is down here, and let me just put it here so you can see it. So you get that pattern, southwest to northeast. So that's the idea of how the Coriolis effect, the rotation of the earth, creates the pattern that our air moves, southwest to northeast, that diagonal line. And you can kind of see that right here, okay, the Coriolis effect. These aren't great because they just show the direction that the air moves. So as it's moving up, okay, it begins to move this direction. It certainly doesn't turn 90 degrees and start going that way. No, it's just a slanted line. And again, you can see them right here as well. And here's even some miles per hour. And you may think, well, why is it different? Well, because at the center where it's the widest, okay, that moves faster than the smaller areas. But that's not important to what we are talking about. But the Coriolis effect, okay, is simply that effect that the wind is moving in a curved line. It's not really, okay, it's really moving in a straight line, but the earth below it is spinning, and therefore gives that illusion that it's moving in a diagonal line. And the proof of that is just simply in our weather patterns, where our rains come from. So that is the Coriolis effect. But again, it's super important that you know this, that you remember this, that you understand this, that if anybody ever asks you, that's what you tell them, southwest to northeast. All right, let me close out the ink tray. Let me slide all this up. And again, super, super, super awesome teacher skills right there. Let me blow this up a little bit here because I want you to be able to see all this stuff, and I got to move this down. There you go. That's some good adjustment. That's some good adjustment teacher skills right there. All right, so what you're looking at here is the 3 types of wind patterns. Oh, let me back up. Hey, be sure that you write this down. Oh, I don't have my ink tray up. Be sure that you wrote that down right there, and that you drew all the things on the globes that I did to try to emphasize the way that the air moves. Be sure you capture all that. All right, now we're talking wind patterns. Okay, and you can see that right here. Along the surface of the globe, there are 3 major areas that create the patterns of the wind. And these are more of the variables that I'm talking about that affect the flow of the air on the surface of the earth, which brings in the clouds or takes the clouds away, that kind of stuff. Excuse me there. All right, so the first thing we have to recognize is that where the hottest area on the surface of the earth is, and hopefully you're able to say that's the equator. Everything forms around the equator, and the fact that it's always so warm, okay, the equator, and hopefully you know this as well, it has lots of rain every day, and that's why they get such all that vegetation, the tall trees, the big plants, all that stuff. It's because they get lots of rain. And they get lots of rain because of this process right over here. Okay, that's called convection. And I'll put that down right here. And again, it will look very kindergartenish because I have to write with the mouse. But convection. Convection, and hopefully you remember this from your middle school days, your physical science days. Convection is the idea of it's a type of heating into which an object, in this case the object is the air, is heated up not by the direct source, which would be the sun, but by the indirect source or the secondary source, which in this case is the earth. And since the hottest area of the earth is the equator, okay, that warms its air up much more than other areas, and that air rises. So convection causes warm air to rise. And that's going to be really key when we start talking fronts. But warm air rises, okay, because it's very light, okay, very light. And in cold air sinks because it's much thick, it's much more dense, and you can really feel that in the wintertime. Because in the summertime, the breeze is really warm, obviously, but it's very light. It's a very calm, it's a very soft, gentle breeze for the most part. But in the wintertime, if you think about it, the wintertime winds, when it's really, especially when it's really cold, it's a harsh, thick, heavy wind. I mean, it can You can even think about sometimes that you just feel like it's going through you, that it's so hard and thick, and that's why. And convection is causing that. Warm air rises, cold air sinks. And I'm going to put a slash because, in other words, like you could use either one of these words. I'm going to put the word replaces. What I mean by that, if the warm air rises, something has to replace it. We always have air moving around us. Sometimes not very much or not very heavy speed, but it replaces it. So in other words, if the warm air rises, other air come in to replace it. So there's always some kind of breeze. Now, sometimes, like I mentioned, it's very, very slow, 1, 2, 3, 4, 5 miles an hour. So you don't really feel that much, and that's not much to actually move trees, branches, and stuff. Excuse me. So there's always a breeze, but like if you look at a tree, sometimes the leaves aren't moving or the branches aren't moving because it's not very fast. But there's always some kind of air moving around us. And so convection, so this right here is a convection cycle. We're at the equator, and here you can see the warm air is rising. Okay, the warm air is rising, and then when it gets up here, it cools back down and falls and replaces, and that pattern replaces the air that's moving up. So at the equator, the air is moving towards the equator, and you can see that over here on these lines. And it's because air has risen, got up here to a certain level, and cooled. Of course, also while it's up there, it makes clouds. All the evaporated water that it carried up with it now cools and turns back into water, in the idea of condensation, and forms those clouds. But then the air itself cools and falls back down because now it's heavy again, and then moves into the equator. And again, that's why these lines here moving towards the equator, because the warm air rises and then it falls and just makes this circle. And then you can see that right over here. Okay, now this second area, okay, and we talked about these. When we talk about these, we'll throw in the actual degrees. But the second belt that causes an effect on the wind patterns is the 30-degree lines. And you can't see that right there, but that does say 30 degrees, but you can see it over here. Okay, that 30-degree line. Now that is where the air starts to fall. Okay, at the equator, it rose and made this circle. Okay, and you can see it over here where it starts to fall is that 30-degree line. And that's what affects us to some degree. We're more the 60-degree line, but we'll get to that in time. So it rises at the equator, which is the 0-degree line, and then when it starts to fall, it's at that 30-degree line. And so here you can see that, and if it starts to fall and to move towards the equator, it moves away from, okay, that 30-degree line. Excuse me. That 30-degree line. And so you can think about the 30-degree line. If you were looking at this particular globe has the opposite side from us. But the 30-degree line it runs somewhere along like Central America, a little bit of Texas maybe, Florida maybe. But that kind of gives you a general reference as to where that at. So if this was the side of the globe that had us, we would kind of be, we're kind of like riding here if we drew the United States as a rectangle. That 60-degree line is kind of the upper part of our part of the world. So we've got this convection cycle. Okay, it rises at the equator or 0 degrees, and it falls at the 30-degree line. And so that's what causes all that wind to move towards the equator. Move towards the equator. All right. So the third area is now the 60-degree line, and it's hard to see it here, but you can see it here. And this is where we come into play. Because look at that line right there. Look at that line right there. What does that look like, or what does that resemble that we talked about up there in the previous section? That's right. That's our wind pattern right there. That is our wind pattern right there. So we're part of this convection cycle right here. So if this air is moving away, okay, so now we got a new convection cycle. So at this area, it's rising. Okay, the warm air is rising and making that circle. And when it cools, it falls. Wait, I'm saying it wrong. Yeah, I'm up too high. That's what it is. I'm up too high. Yeah, I apologize. Let me get that off the screen there. I'm up too high on my diagram here. And I'm going to take out some of those other lines, but that's all right. All right. I apologize for that. I was up too high. But it's the idea of, because it's actually, it's down here. It's this way. So we've got the warm air. Yeah, it's here. Yeah, the warm air rises here. Yeah, let me draw this one. Yeah, now I'm just second guessing myself, but that's all right. I know what I'm talking about, even if it doesn't sound like it. So this is our wind pattern right here. Okay, but again, it's a convection cycle that causes that. So this is the idea. This is a colder area. Okay, that's where the cycle is. So but anyway, this is our wind pattern. And again, I apologize if it sounds crazy, but I drew it in the wrong spot, and it just kind of, my mind went boom, exploded. So this is our wind pattern right here. So this right here explains everything about the way our wind patterns move. And so as we think that southwest to northeast, it's highlighted right here. So these convection cycles create that warm air rising, colder air coming in to replace it, and that's us right here. Everything about our wind pattern is showcased right there. So let's talk about the three types. And I got them listed here, so be sure that you write this information down. And let me close this. I don't think, no, I didn't mean to do that. I meant to close this. I don't think there's more out there, no. Oh, that was when I was looking at that thinking, what did I do that for? That was the Highway 49 example. All right, let me center this back up. So three types of wind patterns. Okay, we're going to start with the first one. And basically we're working our way from the top of the globe. Oh, I don't have my pen. Top of the globe, working our way down into the equator area. And that's why you see the word equator on number 3. So the polar easterlies. This is our winter winds. This is why in the wintertime, not only because the cold air is replacing the warm air that rose, okay, and along the warmer areas behind us here. So you can think of this area, I didn't mention this is like the Mexico, oh, I did mention that, Mexico, Central America area, much warmer than what we have. So it's the idea of the polar easterlies. Let me underline that. That's his upper part, and that's where our cold winter winds come from. And you may think, well, that's a long ways from us. It's true, and what's happening is because in the wintertime when our temperatures drop, because of the tilt, because of the seasons, because of our rotation around the sun, okay, it cools and that wind is allowed to come further down. Okay, come further down. But also, if you think about it, in December, in January, in February, we can have a nice, kind of warmish, 50-degree. It's even been at like Christmas break. We've even had some 60s sometimes. Just nice, spring, almost spring-like days, because it's again a variation of temperature, the tilt, and everything, and nothing. There's just so many variables. But the polar easterlies, that's the wind zone. You can see it here between the 60-degree line, which is here, and you can really see it here. So we're talking this upper cap right here. And then the same thing down below. We're talking this cap down here. And so it's that idea, that's the polar easterlies. It's the winds that are coming from the top, the poles, downward. And in our winter times, our temperatures, as they drop, those winds are allowed to come further down. And certainly the Chicagos, the Minneapolises, the New Yorks, those places, the Bostons, they really feel the effect of those winds. And if you know anything about the snow lake effect, when those harsh winds come across those lakes, and that warm air is rising, man, they can soak up a lot of evaporated water and then just dump snow all over the place below the lakes or south of the lakes. So that's the first set of wind patterns. The second set, which is the ones that affect us, that's prevailing westerly. That's between 30 and 60. So we're talking in this belt right here, and that's us right there. We're in that belt. Those are the westerlies. Those are our winds, and you can see the patterns here. But they're between the 30 and 60 degree line, and of course same on the bottom down here, the 30 to 60 degree line. Okay, but that's us right there. That is our wind pattern right there. So that's why storms come from Oklahoma City, which may be here, to Joplin, which is here, to Springfield, which is here, and then even on to St. Louis. So there have been many cases in the past, and maybe this winter we can watch this, but you can literally see a snowstorm go from Oklahoma City and drop snow all the way to St. Louis and beyond. And if you keep going, you get a little bit of Chicago and Memphis in there, and things beyond St. Louis. But you can literally watch the snow just drop along that pattern belt. And it's pretty cool. I mean, obviously we don't want a bunch of snow. We like to play in the snow. We like to see the snow. But if you got to travel like I do, you don't want stuff on the roads. So that's the prevailing westerlies. That's our winds. And in the trade winds, in your social studies classes, you've hopefully heard that phrase, trade winds, because these are the winds that in the early days, we're talking, the 1400s, 1500s, 1600s, when people got from continent to continent on those big sailboats, like the famous Christopher Columbus story, which isn't as accurate as I was taught when I was in elementary school, as far as who discovered America, which was kind of funny because there's people already here, but that's a whole different topic and story and a different class. But that's the trade winds. These are the winds along the equator belt, and you can see it's that 30-degree line to the equator. These are the areas that people used, and they used these winds to guide them in the direction they wanted to go, because the sailboat obviously needs wind pushing it, and they used the trade winds to get from continent to continent in their sailboats. And you would plan out your trips based on the prevailing wind patterns. Obviously, you can't sail on your boat against the wind. It just doesn't work that way. It's just going to push you backwards. But that's the trade winds, and that's that belt there. So that is the idea of wind patterns. That's the idea of Coriolis effect. And so one more section. Let me close this out here. And for this, we must be... Oh, no, I'm sorry. Oh, I said one more section. I got 3 more sections. Look at me trying to rush us down the road. Let me put this down just a little bit so you don't get caught up in all that down there. But what's down there? Give me an ink tray. What's down there is the purpose of this whole video, and I can't wait to get to that. But there is a fourth wind pattern. We had the 3. We listed 3 up there, but there is a fourth, and that's the jet stream. But it's high in the atmosphere, and hopefully you've heard that phrase, jet stream. But here is a picture of these jet streams along the ones that are towards the top, like this one, and the one down here at the bottom, this one. Those are the polar jet streams, and the ones here in the middle are the tropical jet streams. Those names aren't important, so I didn't put them down, or I'm not even going to write them down, but just to reference what their names are. But the three things about the jet stream, and of course I'm going to be sure that you write all this down. Time for another drink. All right, the three things that you want to make sure you understand about the jet stream is that they're very high in the atmosphere. We're talking 4 to 6 miles up. And that's one of the reasons. There's lots of other reasons, which I will also mention, but that's one of the reasons why airplanes, if you've ever flown an airplane, can you remember the altitude that you were flying at? Okay, they don't fly at 1,000 feet, and there's some safety reasons because of that. But they get high in the atmosphere. We're talking 30,000, 35,000, 25,000 feet up. And that's because if you're flying in this way, it's going to be a benefit for you to get up, 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 and get in this jet stream because it's going to help push you. Okay, and proof of that is if you fly from LA, if you fly from, we'll say, Kansas City, and you go to the East Coast, okay, it's going to take you a couple hours. But when you fly back from the East Coast, back to Kansas City or wherever, St. Louis, whatever airport you used, Branson, Joplin, Springfield, whatever, it's an extra hour or two. Excuse me, because that wind slows you down. And that's your proof of the jet stream. But what you also want to know is the speed. It's a very fast wind. And the speed is determined by the difference in the temperature differences in the wind zones that we talked about up there. So like along the equator, which is obviously right in here. Okay, the equator very, very warm, and winds in this area, okay, those prevailing westerlies, they're cooler. And when that temperature difference is a bunch, the jet streamers are really fast. Okay, when that temperature difference is lower, like maybe in the summertime, okay, so if the equator is always 95 degrees every day, for example, on days that we're 95, which we don't like, or even just 90, okay, it's a small difference between temperatures, and then so therefore the jet stream is slower. But in the wintertime, when again the equator is still 93, 90 degrees, and we're 40 degrees, that's a big difference between the temperature, and it creates fast winds. Okay, small difference, slower speed. And not slow speed. It's never slow as you would think, but slower. And so that's an example of the jet stream. So let me close this, and now we're down to two concepts to talk about. And I gotta scroll out here just a little bit. There's some good teacher skill sets there. And actually, I want to be here, so I got to go just a little bit smaller here, and then I can move this. Oh, I don't want to do that. Now I can move this there. I get all four fronts in, because what we don't want to do. Oh, okay, that was not strong teacher skill. Because what we don't want to do is lose the picture. Because I know you want to see me up in that corner right there. Yeah. And you may have thought of this, but I know what the bio people and the A&P people, I know what they do. They take little Post-it notes and put it over their screen right there, so I don't have to look at that. But I know you wouldn't do that. All right, so now, fronts. This right here is my absolute favorite page in the textbook. And yes, if you're thinking, man, what kind of crazy looking picture is that? It's I shouldn't say a funny story, but I couldn't find those images online anywhere to bring in, and I wanted to use the same pictures that are in your textbook. That way, whenever we look at those and do activities with those, you've got the same pictures. So I essentially just took a picture of the textbook page and then emailed it to myself, and then pulled it into the computer in a paint program and cropped it and everything. And so it's not a great looking picture. It's kind of a brownish because I don't have super bright lights in here in my office, which is, you can see that's where I'm at in my office. You can see all my Royal stuff here, my Chief stuff back here, and if the picture's wide enough, It's actually just right over there. All of my Sooner stuff here. I'm a big Sooner fan as well. I was raised to be a Sooner fan. I didn't. It's what my family did, and so that's what I do as well. But yeah, you can see the Chiefs back here. Let's see, that's like an actual football helmet there, and that one right there, that's the Super Bowl championship hat right there, and that right there, you see that tag right there? That's one of my. I did a tour of the Arrowhead Stadium one time, and that's your little visitor pass tag that's hanging right there. So yeah, some cool stuff back there, and of course their championships, World Series banner right there. And let's see. You can't see the trophy. I'm going to turn and see exactly where it is. It's right above the Christmas stocking. The Christmas stocking is there, and the replica World Series trophy is right there. So enough about all that. All right, so back to our fronts here. What I was saying is this picture's not great looking, and you can kind of see where the, and I'm going to erase this line, but this kind of area right here is kind of faded out because that's where the light that hangs above my desk was kind of shining on. But let me get that out there because you don't need to know that. That will not be on the test, if you were wondering where the light on my office hangs over my desk. I guess I could put that on there, but nah, we won't do that. All right, types of fronts. And this is just amazing. I love this. I love this diagram. I love this topic because it just tells us so much about our daily weather. And when we talk about this in class, we talk about it here obviously, but when we talk about it in class, all the time. Once we introduce this topic, we will talk about it almost every day for the rest of the school year because it's just super important. If you know, and by now we've already started looking at weather maps, and I've already said this in class a bunch of times, I know, and I'll say it a bunch more times, but if you know about the fronts that are coming your way, and of course, again, emphasizing that southwest to northeast pattern, so we're talking the wind patterns. If you're looking at a map in front of you, it's to the left. Things to the left are coming our way, especially if they're to the left and lower than us on a weather map. They are coming our way. But if you know, the fronts that are around you, you can yourself can generally predict what kind of weather we're going to have. So, example, if somebody tells you, "Oh, we got cold air coming in," and you know that we've got warm air here now, then you can kind of generally know what weather you're going to get. Or if someone says, or you read that, "Hey, we got warm air coming in," and you know that we've got cold air here now, you can generally predict what type of weather we're going to have. And that's the things we're going to talk about right now. So we're just going to start here, with this cold front. Oh, I got the eraser selected. So we're going to start talking about here with the cold front. And I've got it written here. So, again, excuse me. So again, be sure you write all this down. Okay, that's super important. But a cold front is essentially, and the diagram tells the picture, is we've already got warm air and cold. Remember, cold air is dense. It's thick because it's heavy. Okay, and that's why the winter winds feel so rough because it's just a heavy air. And remember, warm air rises, and so warm air wants to rise because it's light and fluffy. Okay, and cold air is dense. So you can think about it, warm air is like cotton candy. Okay, cold air is like a brick. Okay, so if I throw a brick at some cotton candy, the brick is going to displace or push up or down the warm air. Okay, so bricks and cotton candy, that's your metaphorical image. So the cold air, as it comes moving in, is going to push the warm air up. The warm air wants to rise anyway, so it doesn't mind at all. But that friction or that rubbing of the two air patterns and all this warm air, remember, it's going to be full of evaporated water. It's going to have lots of water or water in gas state. And when it carries it up and it starts to cool, it's going to form clouds. So cold fronts produce lots of clouds. okay, and also rain. Okay, if you're going to have clouds, you're going to be making clouds. Eventually, you're going to get some rain, but it's a gentle rain, and I even say that right here, gentle rain. So we have cold. If you hear we got a cold front coming in, you can expect, okay, or you can hope for, probably a better way, some really nice clouds and maybe a little bit of rain. Okay, a little bit of rain. And again, be sure that you collect all this information here. But on a warm front, okay, warm front is the opposite as far as air masses. Okay, we've got cold air already, and warm air catches up with it. But because the warm air is soft like cotton candy, and the cold air is thick and heavy like a brick, okay, if I try to move a brick with cotton candy, it ain't going to happen. Cotton candy is going to go up and around, or just going to go around the brick. It isn't going to move the brick. The brick is going to say, no. So the warm air is going to go up, okay, and when that happens, because now it's traveling the full length of the cold air, okay, here it's just pushing it up. It's like a bulldozer pushing things along, but here it's caught up with it and it's moving along, and it creates lots of clouds and lots of rain. And I even say that right there, lots of rain. So on days when it just rains all day long, okay, you can be pretty sure that we had some warm air catching up with some cold air. And that's a warm front. And those two happen in our area all the time. Matter of fact, sometimes we just exchange warm fronts, cold fronts, warm fronts, cold fronts all the time. Now, and these last two we don't see very often. I even mentioned that on stationary fronts, you can think deserts because not much is going on. So you've got these two these cold air, warm air that are basically have collided. Okay, but you think, well, why isn't the warm air going up, cold air pushing it up? That's because, and I mentioned it right here, they're pretty close in temperature. There's not much temperature difference. So maybe the cold air is, 40 degrees, but the warm air may be 50 degrees. So there's not much difference, not much. And think about weight. Think air got weight? Yeah, it's got weight. Barometric pressure is a little bit of that, which is what we're going to talk about next over there. Not much difference, and so neither one, the warm air just doesn't push up like it's supposed to. And a occluded front, and you can see here, creates strong winds, heavy rains, the big hard storms. That's an occluded front, and that's when you have multiple cold air masses that meet, and the warm air gets shoved out of the way. You can think got roughed up and really, instead of just push it up, man, it threw it up in the air. And that is what creates your powerful storms. Okay, your powerful storms. So that's the storms when it comes along and it's a hard rain, it's heavy winds, it's got everything, all the lightning, everything. That is your occluded fronts, and you've had a cold air that a warm air caught up with, but then a cold air that's moving really fast catches up with both of them and pushes the warm air up, basically shoves it up, and generates lots of big clouds. And you can even see the height here. If you ever look at clouds that are just really super, super, super tall, that's what's going on there. And when they get that tall, they can create a lot of things. Even your hailstorms would be a part of that as well. So that's an included front. That's the big heavy storms system which we obviously get in this area on occasion. So that is the fronts. Now, these two, I put these two side by side. Maybe it's two separate ideas, but they play with each other. Play is not the right word. They combined their resources to make a lot of our weather. But it is a variable. So like you could have a high pressure with a cold front, a high pressure with a warm front, a low pressure with a cold front, and a low pressure with a warm front. And these are like not accelerators, but coefficients, probably a better word, but that's not a word you're probably super familiar with. But they basically increase or decrease the weather that we're going to have. So let's talk about them. And again, you want to be sure that you write all this down. Okay. But in a high pressure system, the air is falling. And you can see this arrow here. The air is falling, and I put that right there. And when it hits the Earth's surface, okay, it moves away from the area of contact. And think about a sink. Your kitchen sink. You turn the water on. The water comes down out of the faucet and hits the sink. Well, what does it do? It splashes out everywhere. And that's exactly what the wind is doing as well. It's coming down, hits the Earth's surface, and spreads out. And again, it goes, for us, in our hemisphere, this direction. And you can see that right there. And even this wind that wants to go this way, because the Coriolis effect is bending back. Okay, bending back. You can think about if the equator is right in through here, the winds above this, beyond, had a little freeze there. The wind, and you can see the wind is moving this way, and that's that Coriolis effect going into play. I even put that right there. Gives it that, and there's our southwest and northeast. And so high pressures create nice, clear weather. So if you have a high pressure system and you have a cold front, okay, what little bit of rain, what little bit of clouds you might have had, it's going to reduce that. Okay, it's going to lower that amount. It just makes for a nice day. That's a nice spring day right there. High pressure, cold front. You just get you a nice, pretty spring day. High pressure with a warm front, again, it's going to reduce the amount of rain that you have. So high pressure systems kind of reduce clouds and rain. Okay, they are cloud and rain. They don't remove them, but they just reduce the effect. Low pressure, that's your bad boy right there. Low pressure systems, now the air is rising, as you can see, and I got that right there. The air rises, and other air comes in to replace it. And we talked that a bunch, when we talked about the weather patterns, the air mass movement up above. So this air comes in to replace it, and that creates lots of clouds and lots of rain. So high pressure system reduces weather, low pressure accentuates or magnifies, multiplies the effect. So you get low pressure with a cold front, okay, you're going to have even more clouds and more rain. You get low pressure with a warm front, and you're going to have a really, potentially, rainy day. Okay, lots of clouds, lots of rain. You get low pressure with an occluded front, and man, it's going to rain buckets. You might as well just, bring in the ducks, bring in the dogs, and hunker down and get you a movie on, because we're in for a nice, long, heavy wind and rainstorm. Because the occluded front already is making strong winds, and now if this movement is even stronger, because the low pressure is accentuated, yeah, it's going to be a rough day. So on days, and I think we had one, I'm doing this on the 19th, you're watching probably in November, possibly. But on days where we have really, really strong winds, you can almost think, man, I bet you we've got a low pressure system. If you go check the weather map, it's probably what you're going to see is a low pressure system, but it accentuates, it magnifies. Okay, high pressure systems reduce the effects of precipitation and clouds. Low pressures magnify. And let me close this, and you can see these two, but what's down here below is just kind of a summary of all of them. And let me make this a little bit bigger now that we're looking at it. So you can see the high pressure is moving away, low pressure is moving in, and you can see the patterns. Low pressure moves counterclockwise, high pressure moves clockwise, and you can see that, if you think the equator is through here, and I don't have the pin up, then we're moving that way, but the Coriolis effect is going to make it do that diagonal line. So, Earth Science students, there you go. That is Chapter 12, Section 2, which is my favorite one in the whole book. I've already said that a couple times, but I'll say it again. I love talking fronts because it just, and again, we've started looking at weather maps in class. I've already said it a bunch of times. But if you know what kind of pressure system you're in, or what pressure system is coming, and you know the air patterns that you have, and you can have a good idea of what kind of weather you're going to have. Now, you don't have to, maybe not, you're not going to be a meteorologist by any means, but you can, if you hear low pressure, warm front, okay, you can expect some rain. Okay, you can expect some rain. You hear high pressure, and you automatically be thinking, okay, it's going to reduce. So if the weatherman is saying, oh, it can rain, but then we're in a high pressure, it may rain, but it's going to be a soft rain. It's not going to be a long one. So there you go, Chapter 12.2. Man, I hope you enjoyed that. I hope you liked that. I mean, I love this stuff. I love talking this stuff. It's just because it's just so much about what our environment is in our area. And again, just the idea of being able to understand why things are happening, when they're happening, where they're happening, it just makes it pretty cool. But with that, we will say goodbye. And again, thank you. And until next time, hey, enjoy yourself. Hey, I hope everything's going well. I know when I recorded this back in September, as you can see, we were just kind of really starting to get kind of a lot of cases and the students being pulled out of school because of the virus and everything. And so when you watch this, who knows, maybe it's November, something like that. I just hope it's going well for you. Hope you were safe and sound and everything, and everybody in your family as well. And that you haven't had to miss any time, and hopefully we never went red during that time. That'd just be I know I'd miss it. I mean, I hated it last spring when we didn't have school, and I know school, it's the work and it's everything. But I love being in that room. I love being in room 200. I love talking science with kids and just interacting, asking them how they're doing, what they're doing, plans, weekends, work, and all that stuff. I just like doing it. I mean, I enjoy it. There's not one part of being a teacher that I don't enjoy. But with that, that's enough of that. So until next time, we will say goodbye.